Welcome back. Problem 11-32. So statement is the beam is made from a plate that has a constant thickness B if it is simply supported and carries a uniformly distributed load. Determine the variation of its depth as a function of x so that it maintains a constant bending stress throughout its length. So you can see this is the beam clear where there is a uniformly distributed load W acting. The total length of this beam is L, and at the midsection you have this height is h naught, and this h naught varies at a distance of x. At each distance of x this y varies, so you have to find its this depth y as a function of x so that it maintains a constant bending stress throughout its length. So let's start with the solution. So we know that allowable bending stress is equal to bending moment divided by section modulus, and this section modulus S is equal to I divided by C. Clear? So we will find this M as well as S. So for finding this M, what we will do is that we will cut the beam at a distance of X. So this remaining distance you can see here will be equal to L by 2 minus X, and we will draw this portion over here. So what if I draw this portion over here like this, and there is a uniformly distributed load dotted. If I draw is a dotted, so this will be converted into point load, and this distance is L by 2 minus X. So this uniformly distributed load when converted into point load will be equal to W into L by 2 minus X. And definitely you can see that this load W is applied on this beam. So by using symmetry you will get that the reaction force at this point and at this point will be equal to WL over 2, or you can calculate it by using equation of equilibrium. So you will get both this will be equal to WL by 2 WL by 2. So here you can see we will also having WL over 2. So when you cut the beam over here, so you will be having a shear force clear which is V, and you will be having a moment, reaction moment M. So how you will find this moment? And one thing is that it will be acting at a distance of L by 2 minus X into 1 by 2. Okay, so let this is your point 1. So we will apply equilibrium condition in order to find this moment, that sum of all moment about point 1 is equal to 0, and taking the counterclockwise moment as positive. So first moment is due to this force, and perpendicular distance is this one, and that is producing clockwise, so it will be negative. So I will write it minus W into L by 2 minus X into L by 2 minus X into 1 by 2. 1 by 2. Let me check it again. W in this load which is given as this into this distance divided by 2 plus this W into L over 2 into perpendicular distance is L by 2 minus X minus this external moment M is equal to 0. So this moment will be equal to minus W in by 2 into L by 2 minus X whole square plus W into L by 2 into L by 2 minus X. So we will expand it, minus W over 2, it will be equal to L square over 4 minus X square minus 2 times L by 2 into X plus WL square over 4 minus WXL over 2. So again, if you multiply, it will be minus WL square over 8, clear, plus wx square over 2 minus plus, it will be w lx over 2 plus wl square over 4 minus wxl over 2. So this will cut with this, and you can see these two terms I will bring close to each other. Plus wx square over 2. So if you take the LCM, so it will be 8, and this will be wl square plus 2wl square plus wx square over 2. This will be 2. Okay. So when you solve this, you will get it wl square over 8 plus wx square over 2. So let me check it again. This will be minus. This is plus. Again, you can see this is plus. When this multiply, it will be minus. So make this correction, please. This is, all these are minus. Minus, minus, minus. Now if you further take w over 8 as common, so we will left with l square minus 4x square. So this is the moment m when you cut the beam at a distance of x. Now you have this moment as well, and if you take the cross section at this point, so the cross section of the beam will be like this, will be the y, and thickness is given as b. This is y and this is b. So its neutral axis will be lying at a distance of y by c. So c is equal to y by 2, and its I will be equal to 1 over 12 bh cube. So 1 over 12 breadth is equal to b, and height is equal to y cube. So now section modulus S is equal to I divided by C. So we will write 1 over 12 by cube over y by 2. Clear? And from here you will get section modulus will be equal to by square over 6. Now you can apply bending stress. We know that bending stress sigma allowable is equal to moment divided by section modulus. So moment is given as w by 8 into l square minus 4x square divided by section modulus is by square over 6. So if you further simplify it, you will get sigma allowable will be equal to 3w into l square minus 4x square divided by 4by square. Let this is your equation number 1. Now what if x is equal to 0? Then at that you can see that y is equal to h naught. So if x is equal to 0 at this point, you have height of this beam is h naught and thickness is again b. Clear? So we will write it at x is equal to 0, y is equal to h naught, put in equation 1. When you put it in equation 1, sigma allowable, this will be equal to, x will be equal to 0 and y, so it will be 3wl square minus 4 into 0, which is 0. So it will be the same 3w L square. Okay. 3wl square over 4b h naught square. Let this is equation number 2. Now you can see equation number 1 is also sigma allowable, and also equation 2 is also sigma allowable, and it is given in the question that it maintain a constant maximum bending moment, stress throughout its length. So what we will do is that equate 1 and 2, we get, what we will do is that we will equate 3w into L square minus 4x square divided by 4by square is equal to 3w L square over 4b h naught square. So we are interested to find out this y. So we will left this y square will be equal to 3w L square into 4b divided by 4b h naught square into 3w into L square minus 4x square. Okay, so if you further simplify it, you will get at the end y square is equal to h naught square over, sorry, no, I have made a mistake. This equation is not correct. Again, it's happened while you solve this problem by yourself. This y will go there. So y square is equal to 3w into L square minus 4x square over 4b into 3w L square, and we will have 4b h naught square. So 4b will cancel with b. So we will left y square is equal to 3w 3w will be cut with each other. So we will left with the L square minus 4x square into h naught square over L square. Okay, so if I further simplify it, h naught square over L square into L square minus 4x square is equal to y square. So this is the height of y with respect to x, and that is the variation of height with respect to x. Also, if you further simplify it, so y square over h square is equal to L square minus 4x square over L square. Clear? Okay, so from here you will get y square over h square is equal to L square over L square minus 4x square over L square. So y square over h square is equal to 1 minus 4x square over L square. So rearranging them, y square over h square plus 4x square over L square is equal to 1, and this is the equation of semi-elliptical shape. So the beam has a semi-elliptical shape. So we need our answer till this point. So this is the variation of y with respect to x. If you know the value of x and all other parameters, you can find the value of y at any instant of x. So this was all about problem 11-32. I hope you have enjoyed this video and you have learned much of thing from this. Those who are new to my channel, then subscribe it and press the bell icon for getting the upcoming latest videos. If you have any question, you can ask me in comment section. Thank you for watching.